My name is David Fernández-Blanco, and I'm here to talk about a work that I did in my master that is called Anticline growth by shortening during crustal exhumation of the Moroccan Atlantic margin. Thank you, Wayne, and the organizers, and please accept my delivery of this work in video, so I can rest with this QT for longer and ahead the mind. To mention is that this work wouldn't have been possible without the collaboration of my co-authors that are listed here, and nor without Giovanni Bertotti, who is the leader of the project and got the funding. The project took place in the Vrije Universiteit in Amsterdam and then eventually in the Technical University of Delft, and it was funded by ISIS, and obviously the publishing organism and not the terrorist group. I'm going to I want to show first is this map of Northwest Africa, where we can see the Moroccan rifted margin. The brown areas here are the Paleozoic rocks that were stable during the Mesozoic era, but were uplifted and inverted during a period of intense geological activity that is commonly known as the Variscan orogeny. The Mesozoic rocks are shown in patterns and include the High Atlas and the rift domains, which were involved in the extension of the Atlantic margin and were rifted during the late Triassic and Upper Jurassic. The map also shows the different parts of the rift margin, including in yellow the coastal basins of Mesozoic rock, the continental shelf and the slope domain in different colors of blue, and the West African coast magnetic anomaly that is shown in dark gray. What is important to note here is that during the late Jurassic to early Cretaceous, the rift margin experienced an unusual period of early post-rift subsidence, which caused the coastal basins and the continental shelf and the deep basins to lift up and erode areas to the east. Low temperature thermochronology have shown that this uplift event affected most of the Precambrian Paleozoic rocks to the east of the rift margin, so this region over here. This anomalous uplift event occurred between 30 to 50 million years after the lithospheric breakup and separation of Morocco and Nova Scotia, but before the Alpine contraction. In the Western High Atlas, there is a well-preserved Mesozoic rock sequence that is useful to study the geology of Mesozoic basins that are shown in yellow in the map. Sarira Basin, that is shown here in green, is one prominent basin among these ones and developed as part of the Atlantic margin during the Triassic to early Jurassic times. Then it became a shallow water platform of the Atlantic passive margin from the Middle Jurassic onwards. Now, in the Essaouira Basin, there are several salt anticlines that may help us understand the process behind the uplift during the post-rift phase. So it is important to determine whether these anticlines are or not related with salt deposits. And seismic observations support that these salt anticlines were formed by salt withdrawal during the Tertiary period and were later affected by the Alpine contraction. We wanted to check whether this was the case, and for that now we use a detailed structural fieldwork. Again, to reiterate the questions that we had in mind were like, how did the anticlines form and whether they are salt driven? And then once those questions are solved, how they relate with the Cretaceous uplift of the Precambrian domains. Now, I'm going to be centering my attention in this anticline specifically, And then I'm going to show a few observations of all the two for the discussion. But the detailed structural fieldwork that I did for my master took place in this one, in this structure that is called the Jebel Amsitene Anticline. The Jebel Amsitene Anticline is relatively small and has a good exposure of rocks from the relevant time period. The oldest formation, which lies in the core, consists of deltaic sandstones and evaporites from the Upper Triassic period, and you can see it here in pinkish. And this is followed by a complete sequence of Jurassic to Lower Cretaceous rocks that are then covered by the Quaternary deposits. Gonna level to notice is the JC level. This is the first green level that we have in the map, this unit over here, which marks the transition between the uppermost Jurassic and the lowermost Cretaceous periods. And what I will show from now on is a standard structural field study with several cross sections and field evidence, nothing fancy. We found on the Jebel Amsitene Anticline, we found in this western region of the Anticline, and with them we did the cross section A. What we can see here is that in the southern flank, that is here to the right, we see the early Cretaceous to Middle Jurassic layers that are deep in south and become horizontal or slightly north deepen in the highest area, so around here. And then they transition from horizontal to overturned layers here in the oldest rocks that are exposed. So overall, what this section shows is a northward tilting anticline with a plunging head shape that is located here in the central sectors. What I want to show now is a few pieces of evidence in the limestones of the lowermost early Cretaceous to uppermost late Jurassic unit, this JC unit that I said was important to keep track of. And in the image to the right, what we see is one of the three conjugate sets that we found in an outcrop in this unit. And they all show similar orientation with regional bearing gently dipping south-southeast and clear striae with horizontal or overall south directions. Conjugate faults are caused by horizontal stresses and are mainly oriented in a north-south to north-northeast, south-southwest direction. This holds true for both the pre-tilt and the post-tilt rocks, so whether you correct or not for the regional bearing in your measurements. And the image to the left shows a sedimentary ramp fault in the same unit, just a few meters away. The fault is verging north and shows soft sediment deformation. This structure implies north-northwest, south-southeast shortening during sedimentary deposition. So now I will show a couple of observations near the salt. The Upper Triassic salts are seen outcropping in a circular depression of approximately 1 kilometer of diameter in this region of the Anticline. The Jurassic rocks around that salt, and this is seen here in the right, dip consistently away from the salt in an overall concentric configuration. The dips vary from subvertical to near 25 degrees, farther away from the salt, and the strike directions gradually change to a regional east-west to southwest-northeast trends in about 400 meters away from the salt in any direction. So if we continue moving along our cross section and for about 500 meters, the overturned strata become more vertical, and finally dips towards the north. Now, the sequence of south-southeast Virgin fault propagation faults that we see in the outgroup in the lower Jurassic unit have axial planes that indicate south-southeast, north-northwest shortening. So these are clearly non-extensional structures that are near the salt and that show the opposite vergence. Shown here is situated about 4 kilometers away from the previous one and is parallel to it. It has a comparable but a bit less pronounced structure with layers dipping gently towards the south, as we can see in this region over here, and overturned towards the north, as it starts to be here and there. This section displays the variation in thicknesses of the uppermost Jurassic to lowermost Cretaceous rocks, with layers being consistently thinner in the north than they are in the south, and with differences of about 350 meters, from 350 meters here to 900 meters here. This is another cross-section that is located farther to the east, again around 4 kilometers away from the previous section. What we can see is a northwest sloping anticline with a steep northern flank and a gentler southern flank. There aren't many great exposures of rocks in this area, but we can still observe differences in thicknesses in the JC formation. The southern flank, this formation in the southern flank is around 550 meters thick, and in the northern flank this is 400 meters. On the contrary, like the thicknesses of the other formation, all the formations that are older remains consistent. Between the second topographic high and the valley north of the Jebel Amshaten Anticline, upper Middle Jurassic, which is J3, to lower Jurassic, like the C1 unit, layers are tilted northwest at a steep angle of 60 to 80 degrees. And north of the valley, we can see the layers from the lower Cretaceous, C1 to C3, with a gentle tilt of 10 to 20 to the north. What we can see is a couple of reverse faults that are indicative of sedimentary deformation. The structure dips to the southwest and offsets these layers for about 20 centimeters and terminates in the overlaying slump sediments, which are clearly showing soft deformation. This type of fault is an indication of deformation that occurred while the layers were being deposited or being formed. Another structural observation that we found in the lowermost Cretaceous limestones is located here, around 5 kilometers away from the cross-section C. And what we see there is a series of reverse faults with high angles that are dipping towards the south-southwest and terminate against this overlying wedge of the formed rock that is about 30 meters long and narrows towards the south. These are top to the south of faults that show reverse motion of a few tens of centimeters. And the slick slides that we see there indicate that the rocks were shortened in the south-southwest to north-northeast direction. The relevant part is that these faults are terminating in the syntectonic unit, obviously, indicating a deformation during that period. Show the differences along the strike of the structure. I'm showing here the three profiles that we just saw and two other profiles that are located farther to the east. And what I want to show is how the profiles to the west show tighter structures with a clear north vergence and deformation with diaparism near the hinge, which is prominent when you are close to the salt. But the northern limb is frequently overturned, displaying this plunging head shape north of the topographic high. And in these sections, strain markers are numerous and layers often change deep in direction of the short horizontal distances. Now, if we move or we mention about the eastern profiles, they show a more open structure, which is smoothly asymmetrical anticline, which are less clear north versions. And here the salt deformation is barely noticeable, and the northern limb shows no overturned layers. The layers along the limbs are alternating sectors of constant dip with others where they vary basically in a progressive manner. The anticline axis is plunging towards the east, and the style of deformation changes laterally from this box pole with a plunging head and widening into an open fold in the east. The amount of shortening decreases eastwards from approximately 25% in the west to around 4.5% in the east, and the thickness of the uppermost Jurassic lower Cretaceous formations also vary laterally, with maximum thicknesses in the cross sections B and C between the southern and the northern limbs. To summarize the field data that I've shown so far, revealing a north virgin salt core fault propagation fault, with the Triassic salt acting mostly as a detachment plane. Regional kinematic indicators and structures suggest overall shortening in a north-northwest, south-southeast to north-northeast, south-southwest direction, with active tectonics during the post-reef phase, as is evidenced by the syntectonic wedges observed during the late Jurassic to early Cretaceous period. All the observations that I've shown so far are indicative, are refuting the idea of salt drive tectonics and are favoring the idea of tectonic drive salts. And if that were the case, this would be indicative of factors other than small cell mantle convection as drivers of the evolution of the Moroccan Atlantic rifted margins. Now, to try to further constrain this question, we can have a look at other anticlines that are also believed to be formed by salt diaparism during the late Cretaceous. The following observations all come from Mohamed Gouissa's PhD thesis, and I'm going to take full advantage of the video format and provide you only with the upper super succinct version of what's the story that those anticlines have to tell. Perhaps the video and the images in the video can help Mohammed to be able to give more details if they are needed, as I believe he's in the audience. So this, as said, these anticlines are thought to be formed as well by salt withdrawal and with evidence of it during the late Cretaceous. Now, but some other deformation that is tectonics have been shown, or Mohammed showed, for the lowest Cretaceous as well. And in this case, what we see here is a full verging towards the core of the anticline, so not allokinetic. Other observations from the imitanute wedge are in the imitanute wedge is that the thicknesses of the post-reef formation are gradually increasing from northeast to southwest and reach over 300 meet us near the coast, and that the wedge is opening along a north-northwest, south-southeast to northwest-southeast axis. So with all this evidence, we hypothesize that the mantle convection of far-field stresses may be responsible for the observed deformation features. And mantle convection could have weakened the lithosphere, making it more susceptible to deformation. And meanwhile, far-field stresses may have produced the observed compressional features. If we see these images that are showing how plates move during the opening of the South and North Atlantic Oceans from 125 to 85 million years ago, we think that the changes in plate movements that these reproductions are showing are compatible with our structures and cause the shortening features in the Western High Atlas. Finally, I want to close. So I wanted to finish with these images, these photos of the different members of the team. I want to thank you everyone for following along. And if there's time for questions, I believe Mohamed Guisa is in the audience to answer them. Thanks for everything. Bye.
Okay, thanks Mo for playing the video. So apparently you are supposed to answer questions. So do we have questions in the audience? Someone would like to raise her hand? If there is no question, I just have one quick one more. David is opening at the end on the crystal structure. Do we have any constraint on the crystal thickness under that kind of basin?
Not really. I mean, there is some work that's been done. I mean, there is like a long, quite regional refraction line that crosses the atlas. There is also some numerical modeling that's been done using gravity and to try to model crystal thicknesses in the entire that region, actually, from North West Africa. And crystal thicknesses, the current crystal thicknesses are around between 36 and 38. In some places they can go up to 40 kilometer thick. So so that actually, like, yeah, I mean, it counts for the shortening, the alpine shortening.
Right. Okay.
That actually those thicknesses are, yeah.
Interesting. Yeah, exactly the same type of crystal thicknesses we have here in Norway, where we observe also rift basins. Okay.
Yeah.